Hi everyone. I'm going to just briefly go over this and make sure that you have enough that we can go off of and do something tomorrow when I get back. This shouldn't take 15 minutes, I'm hoping. So, 3.1, Chapter 3. We've got functions that have got extreme values. So, those Extrema where you're looking at like the maximum values and the minimum values. We're just going to get more in depth as to what those really mean and other ways we can possibly find them. So real quick, an absolute or global Extrema is the largest value of a function on its domain. So if I've got a quick little something like that, this is the largest maximum. You have other maximum values, these guys, and we'll get to what those mean in a second. But the absolute or global maximum is that largest value, and the absolute or global minimum is the smallest value. So if I were to like change this guy a little bit maybe and pull him down pretty far, there we go. Now he's definitely the absolute minimum. So that's all that means. So if we've got this function right here, cosine, just cosine, and we're restricting the domain between negative pi over 2 and positive pi over 2, what is the absolute maximum and the absolute minimum? Well, if you remember cosine, let's make a quick graph for it. Cosine is the one that starts at 1, and then at pi over 2, you go down to 0. And then at negative pi over 2, you are also down at 0. So if we're restricting the domain between those two values, you're going to come up and then down, just like that. So the absolute maximum, just based off of the graph, is at x equals 0 with a value of 1. I mean, like, we could have figured that out just based off of what cosine is. Cosine's only going to be as big as 1 and as small as negative 1. But we weren't sure what the range was, right? Because if this was sine, well, it would have worked for sine anyway. But still, besides the point, we know it can only be as big as 1 and as small as negative 1. Now, here, the interesting thing is the absolute minimum. You actually have two values here that are the same. Your absolute minimum can occur twice if it's the exact same thing, and that's okay. You would just say our absolute min is at x equals negative pi over 2 and pi over 2 in this case, because they are the exact same thing. They are the smallest this function gets on this domain. Remember, we are restricting this domain. And has a value of 0. Okay, but it's not always the easiest thing to do to figure out, because I know you guys love graphing sine and cosine so much. I'm going to give us an option that lets us not have to actually know the graphs of these functions off the top of our head. I'm going to, show you how we do it with calculus. So, I forgot about this part. Sorry, a little foggy. The absolute extrema of the following functions. It's just the same function, right? But your domain is a little bit different. If your domain is all real numbers, you guys know what x squared looks like. The absolute minimum, not maximum. The absolute minimum is 0, 0. And there is no maximum because it's just going to keep on going up. Here, your minimum is still 0, 0 because you have 0 there. But then your maximum is at 2, 4. And that's because that is as far to the right as you can get. Here, there is no minimum, and genuinely that's just because it would be 0, and you can keep getting close to 0. You can get as close to 0 as you want. 0, 0, 0, 0, 1, like you can get really close to it, but that's still not the smallest value, because right here I've just come up with another one that's even smaller than that. So there is no min, but the max is still at 2 comma 4, because that is the largest you are going to get at 2, and you can actually plug in 2. And as you might have suspected, the next one has no maximum or minimum, because the domain does not include the endpoints. We are not including that 0 or 2. So moving on from that, this is where it's all at, the extreme value theorem. Okay, if you've got a function that's continuous, then that means it can be differentiable. Remember, continuity means maybe differentiability, but it needs to be continuous if it is differentiable. If it's continuous on a closed interval, whatever that closed interval is, then f has a max and a min value on that interval. So if I gave you any function, I said, here's a function, f. It's on this interval, a to b, whatever that interval is. I don't care what numbers you're using in your head. It will have extrema. Well, that's not what I meant. Extrema. Right, so I'm going to zoom in really quick. I wonder if this will show up as me zooming in. I really hope so. So if I've got this function f on this interval x2 and x1, or the interval is a to b, and then I'm looking at these two x values, x2 and x1. On the interval a to b, there has to be a maximum, there has to be a minimum. Same here, as long as we include the endpoints a and b, we actually have those extrema. The difference was with the problem in the last slide is we would have had a situation like this, where a and b is not included, and then there is no extrema. Remember, it's got to be a closed interval a to b. Here you have a maximum in between your interval, and then you have minima at the endpoints here, and that's okay. You can have minima on both your endpoints. This is your absolute minimum. We'll get to this I think in a different section actually, but that is also technically a minimum. So let's see. And last, but this one right here is just the inverse of this guy. Right, you have a minimum on your interval a to b, and then at your endpoint you have your absolute maximum. That's really all it means. If you have a function with a closed interval, there you go. You have at least one max and at least one min. You will have both if your interval is closed. Excuse me. Excuse me. So now we're going to talk about the thing that I think is more interesting, is local extreme values. And local extreme values is just not necessarily the largest or the smallest, but it is, if you were to restrict your domain, it would be one of the largest or one of the smallest. So right here, you've got this local maximum, okay? And that's because, let's say, for a second, I'm only looking at this little piece. If I'm only looking at this little piece, then this piece would be the largest. Another way to think about how to find these things is that it goes up and goes down. That's a maximum. That is something I think I showed you in pre-calculus. It's the exact same thing here. Again, the reason why is that if you just cut off the rest of the function and looked at that piece, that is the largest piece. If you look at this piece over here, you ignore the rest of the graph, then that is the smallest piece. And granted, of course, you do have the absolute extrema still right here and right here. All right, this is the largest the entire function gets, and this is the smallest the entire function gets. And even if it doesn't go down and comes back up, that doesn't mean it's not a minimum. If you were to, keep on restricting the domain even by a large amount, it's still the smallest. So that would also be a local minimum as well. We'll redefine it better, but basically because it's going down and then stops, that's a minimum. That's really it. If it were to look like this would be a maximum. This would be a minimum. Or if it went the other way around, this would be a minimum. This would be a maximum, even if this was an endpoint, because you were going up. It really just depends on which way the function's going at the given time. Excuse me. So if I happen to call them relative extrema, that's why right here, right, they're also known as relative extrema. I don't know which one your textbook prefers to do. I'm just going to keep calling it relative extrema, or local. I'm going to switch between the two. So, if you want to find, this is the big one. If you want to find where the extreme values are at, the derivative 0. I was going to do a big build up towards this, but I don't want to. So let's take a look at something easy like this. If you keep on looking at your tangent lines, the closer they get to your extreme value, the closer and closer they get to actually being flat. And remember, your tangent lines have a slope. The slope of these guys at the extrema is 0. But if your tangent line is 0, that means your derivative is 0. That's really all it's saying. So formally it says if a function f has a local max or min, and remember, and this does say local, so this works at any extreme that we're dealing with. If it's at a point C, and then your derivative is 0 at that point. That's really all it's saying. Let's take a look at a quick example. Right. Just kidding. That's a definition. Let's look at a definition real quick. It's a critical point. The critical point is essentially where it's not called a critical point for no reason. It's called a critical point because something critical happens there. Go figure. Right. The important thing that happens there is either your derivative is 0 or does not exist. That is a really important thing because not all maxima, not all minima are going to necessarily be a nice tip to a nice hill or a crevice in a valley or something like that. They're not all going to be like that, right? You might end up with the absolute value function. This is still a minimum. The derivative does not exist there. If you remember, we did do something like that, where we looked at the absolute value of x and how f prime of 0 does not exist. And that's okay. X equals 0 is still, I can't spell today, is still a critical point, and that's okay. That's fine. Essentially what you're going to do is when you take your derivative, you're going to find domain errors. Those domain errors are going to be where your derivative may not exist, and that's okay. If your derivative doesn't exist, you go, that's a critical point. You might have to graph it to figure out how big it is, but also you might not have to, and that's okay too. We'll get more into that as we get into it. So real quick, I think I'm going to take a peek ahead. I think I'm going to do these two examples and call it. I'm at 13 minutes. We're going to try and do this quickly. If you need me to go over any of it any time, send me an email. I'd be happy to. Right here, we're trying to find the absolute max and min. So we have our new theorem. Take your derivative. That is 2/3 x to the negative 1/3, which is 2 over 3 cubed root of x. Totally okay. That's fine. This guy is only going to equal 0 when the top is equal to 0, and I don't know about you guys, but I don't think 2 is ever going to be equal to 0, which means your function's never going to be equal to 0 here. But at the bottom right here, we could have 0 in the bottom, which is a problem, which means your derivative doesn't exist at 0. So there's a critical point. There's a critical point at x is equal to 0. But we also need to be mindful of our domain here real quick. Always double check that where you're going to have the problem is even a part of your domain. 0 is on the interval -2 to 3, so there we go. But one thing we also have to worry about is the endpoints right here. The endpoints are also critical points because we have some sort of function like this, but we're cutting it off early and we're starting it late. So we have those endpoints there. Those can be extrema as well. So we have the potential for 2 more critical points, and that would be at x equals -2 and x equals +3. If you want to know what the value of these extrema are, you need to plug them back into the original function, and be really careful about what I just said. You plug that back into the original function to figure out what the actual value is. This guy gives you slope values. You want to know when it's going to be 0. This guy gives you y values. That tells you how much of a maximum and how much of a minimum it is. So if you plug in like f of -2, you get the cubed root of -2 squared. That is what it means to raise something to the 2/3 power, which is the cubed root of 4. Oh, I don't have my calculator. Hold on. I mean, you guys probably can figure out what the cubed root of 4 is really quick. Cubed root of 4. Help me out, Google. 1.587. Cool, sick. And then you've got f of 3, which is the cubed root of 9. Remember, it's just 3 squared, so we got the cubed root of 9. Now I have it pulled up. We're ready to go. 2.0800 actually, so I guess we'll just call it 2.080. And then we have f of 0, which is 0. Okay. Now the question that you might be wondering is, okay, great. How do I know which one is the maximum, which one's the minimum, and especially this guy right here? Because, I mean, you'd think he's the smallest, and I mean, between these two, you'd be right, but that doesn't mean necessarily he's a maximum or a minimum. So we just have to be careful. The way we can do this is by going in, making another number line, and we are going to put those. The important one is at 0, right? We want to know what it's doing around there. You can look to see what's happening at -2 and -3, or I'm sorry, +3 as well. But really, we're interested on the interval between these three because nothing is happening over here for our function. We've defined it to be the interval -2 to 3. So you don't really need the -2 or 3. I always put them there. It's just a habit. And what we're going to do is we're going to plug in something in between -2 and 0 to figure out what our function is doing, and we want to know whether or not it is increasing or decreasing. So what we're going to do is we are going to, I'm going to plug in -1 because, I mean, I think that is easiest. -1 squared is 1, cubed root of 1 is 1. That is positive. Wait, no, Mr. Morrison did it again. We're trying to figure out whether or not our function's increasing or decreasing. That means we have to look at your derivative function, because your derivative function gives you intervals of increasing and decreasing, which is a bit of a spoiler, but it's fine. Again, if you plug in -1, this time it'll actually be negative because the cube root of a negative is a negative. And then if you plug in a positive, you get a positive. So at 0, because you're going down and then coming back up, this is a minimum right here. This will be a maximum, as will that. So your absolute minimum is right here, and your absolute maximum is right here. Come to think of it, they did only ask for absolute max and min, so all you need to do is find the largest and smallest values because they only wanted the absolute max and min. I also just spoiled how to do the rest of it, so there you go. Real quick, we'll do this guy. Not the nicest derivative, but we'll be fine. We'll take our derivative, f prime of x is equal to, well, actually, real quick, before we take the derivative, let's rewrite this guy. This is gross. So we've got 4 minus x squared to the -1/2. Right? If you've got a square root in the bottom, it's just a -1/2. Negative because it's in the bottom, 1/2 because it's a root. And then your derivative is going to be -1/2 times 4 minus x squared to the -3/2. Subtract your 1 from your exponent. That's just power rule. But this is a chain rule, so it's -2x as well. I'm going to clean this up a little bit. -2 and a -1/2. That's just 1. So we end up with x over the square root of 4 minus x squared quantity cubed. And that might help us. I don't really know. We want to know when this guy is going to be 0. It's going to be 0 when the top is 0. So we have to say, hey, you have a critical point at x equals 0. But then we also have to figure out where our derivative is going to be non-existent as well. So we want to look at the bottom here, and you want to say, hey, when is 4 minus x squared going to be equal to 0? And that's just a difference of squares. So it's going to be 2 and negative 2. So you have a critical point at negative 2 and at positive 2 as well. If you want to figure out what these values are, we can always plug them back into the original function. So you plug in 0, you get, what would that be? Is that really just a fourth? No, it's a half. So one of our points is 0, 1 half. This is one of our extreme values. Let me actually label that. Let's just say, hey, these are the extreme values. It doesn't ask for whether or not they're absolute max or min, so I don't care. I'm giving them what they asked me. That's, oh God, Freudian slip, sorry. And then you've got Extrema. Right, we're just saying, hey, here's my Extrema. And then you've got 0, 1 half. That is the extreme value. At negative 2, you have does not exist, right? That is a function that does not exist at negative 2. And then at positive 2, it also does not exist. So really the one extreme value that we really care about are those two. These don't have values. They're actually not a part of the domain even, so we can't do anything with them. Now, it's important to note they are still critical points, but they're not really extreme values because you can't plug them back in and get anything. So really, there is only one extreme value. It's at 0. You get about a half back. I'm going to stop there. I think that is plenty for you to work with. I'm going to post some homework for you to do. Excuse me. And I would like you to actually try at least like 2 of them. So that way, if you have questions on anything that I've just done, we can start with that first thing tomorrow morning. I will be back tomorrow. I might not be the most like alert. So if I make mistakes, let me know. If I made mistakes during this, send me an email. I'll fix it. That's all I've got. Hope you all have a good day. Happy Thursday, I think. So I'll see you guys later. Okay. Bye-bye.